So in previous lessons, we have talked about solving systems of linear equations, certainly. Today we're going to continue that conversation and kind of talk about some relationships and some observations we can make about those solution sets and also about what they represent. So to do that, we're going to talk about something called a homogeneous system. Now, a homogeneous system, and some people pronounce it homogeneous. As far as I can tell, they're the same thing. So either way is fine, but I tend to pronounce it homogeneous. Um, so homogeneous or homogeneous means that the right side of the equation is the zero vector. We haven't really solved any of those. It's not that I can think of. But we are now. So the idea here is that it's still a system of equations, but now each equation is equal to just zero. So this is what the equation would look like in matrix form. Here's what the same equation would look like in vector form. Remember, they both translate to the same augmented matrix. The only difference is because it's homogeneous, when we augment that matrix, the right side would just be a bunch of zeros. Okay, so here's the thing. This system always has at least one solution. Because think about it. If this x was a zero, and this x was a zero, and this x was, and they were all the x's were zeros, certainly the result would be the zero vector. So a homogeneous equation always has at least one solution where all the variables are zeros. And we call that the trivial solution. Okay. So trivial just means all the variables are zeros. So theorem. The homogeneous equation ax equals 0 has a non-trivial solution if and only if the equation has at least one free variable. So remember, we've talked about how when we're solving systems of equations, we have three different possible outcomes. Either there's a unique solution, multiple solutions, or no solution. Well, for homogeneous, we're ruling out no solution. Okay, so because there's always at least one. If it's a unique solution, then it will always be that trivial solution. If there's only one solution, it's going to be trivial. So this is saying that if there is a non-trivial solution, the only way that's going to happen is if there's at least one free variable. In other words, if there's a non-trivial solution, then we must be in the case where there are many solutions, where there's a free variable, where, so that's what we're talking about here. So either there's one solution, meaning it's trivial, or there's many solutions, and in which case we've got those non-trivials. So the homogeneous equation either has one trivial solution or infinitely many solutions, one of which is the trivial one. So let's describe the solution set of this system. So let's write the augmented matrix. So there'll be 3, 5, -4, and then of course the right side is 0 because this is homogeneous. Yeah, -3, -2, 4, 6, 1, -8. I think we've done enough of these row reduction or row operations that I'm going to go ahead and just verbally say what I'm doing without actually writing out the notation. So the top row is fine. I'm going to add the first and second rows. So we get 0, 3, 0, 0. And then I'm going to multiply the top row by -2 and add the bottom row. So top row times -2 plus the bottom row is 0. Top row times -2 plus the bottom row is -9. Top row times -2 is 8 plus the bottom row is 0. And then, of course, the right side is just going to be 0 again. Okay, let's see here. I'm going to do a couple of things. I'm going to leave the top row alone for a moment. The middle row I'm going to divide by 3. And please notice that the second and third row, basically if I took the second row times 3 and add the bottom row, I'm going to get a bunch of zeros. So I'm going to put those zeros on the bottom. Okay, so here's our echelon form. Now to get this into reduced echelon form, I'm going to basically take the middle row times -5 and add the top row. So I'll get 3, 0, negative 4, 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay. Let me see here. And yeah, I think I'm gonna do one more thing here. I'm going to put this into reduced echelon form. The only reason, and by the way, that's why I did that last step also, was to put this to here. We've got this 1 in our pivot, and we want to get a 0 above it. So we're continuing to get reduced echelon form. All we have left to do is take the top row and divide by 3. So we get 1, 0, negative 4 thirds, 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay. So there's my reduced echelon form. And yeah, it's annoying that it's got fractions, but that's okay. Now, let's write out what these equations tell us. The top row says that x1 minus 4 thirds x3 is equal to 0. The second row tells me that x2 is equal to 0. Okay, let me, all I've done now is taken the reduced matrix and rewritten it with my variables. And now let's identify what my 3 variables actually are equal to. Let's actually write out the solution. So the top row tells me that x1 is equal to 4 thirds x3. The second equation tells me that x2 is equal to 0. And we can already tell that because there's no pivot in the third column, we know that my x3 is going to be a free variable. Now, some people might just write the word free for x3, and there's nothing wrong with that, but I think it's going to be more convenient if I just say x3 is equal to x3. And the reason I say that is because now, if I were to write my solution as a vector, so here's my vector x, I can see that my first variable is 4 thirds x3, my second variable is 0, and my third variable is just x3. And then one last thing I'm going to do, I'm going to take out that x3 that each of them is being multiplied by. And so I'm left with a vector 4 thirds, 0, 1. Okay, we're going to talk about the solution in just a minute. But the idea here is that my solution, my vector, if you want, my solution vector, can be written as this vector, 4 thirds, 0, 1, times some variable x3. Okay, and x3 can be anything. X3, by the way, x3 could be 0. If x3 was 0, that would be our trivial solution. X3 could be anything, right? X3 could be 3, and then the fractions go away, which would be nice. But the point is, every one of my solutions is in that form, where it's 4 thirds, 0, 1 times some other variable. And in fact, if we wanted to, and again, we're going to do this in just a minute here, if we wanted to, we could rewrite this as 4 thirds, 0, 1 times t, where just like in the previous line, x3 can be anything. T also could be anything. The only reason I picked a different letter t is because that t is going to be what we're going to call a parameter, and we'll get to that in a minute. But the idea of a parameter is it can take on different values, and different values of the parameter result in different solutions. So the different numbers I pick for t would give me the different solutions. But again, there's nothing wrong with leaving x3. It's just now my x3 is the parameter. Now my x3 is I get to pick whatever I want. But let's think about this also. Notice that every one of my solutions is some multiple of 4 thirds, 0, 1. Now think about that for a second. What do we get if we take a vector and multiply it by some scalar t? Well, the result is a new vector that's the same direction, just a different length. So notice that every single one of my solutions is going to be the same direction as 4 thirds, 0, 1, but the length will be different, right? Or if t is negative, it goes in the opposite direction. But the point here is because we had one free variable, we ended up with one parameter t. And because we had one parameter t here, the result is going to be a line in R3. Again, it's a line because it's all the vectors that are multiples of that vector 4 thirds, 0, 1. So I should say, and to be a little more precise, and I'll do this in a couple minutes here. To be more precise, it's a line that passes through the origin, right? Because it's if we put that vector starting at the origin, it's all different lengths of that vector. Anyway, so that's an interesting observation here. If we have um, one free variable, we have one column without a pivot, then we end up with a line. And if we are thinking about the solution as a geometrically in R3. Okay, let's try this one. This is a fairly uninteresting system of equations because there's only one of them. Um, so let me just point out that I could take this equation and solve it for any one of my variables. By the way, something came up on office hours where a student asked me, when we have a free variable, like in this last example, when we have a free variable, does that free variable have to be x3 or could it be something else? And the answer is technically it doesn't have to be x3. Um, it's going to be easier if you pick x3. It's going to be easier if you pick the free variable to be that column that has no pivot, but it doesn't have to be. Okay, I really do encourage you to do it the same way that I'm doing, but technically it's not necessary. So for example, on this one here, whoops, on this one here, I'm going to solve for one of the variables. There's nothing that says which variable I have to solve for. Our solutions will look a little different depending on the choices we make, but you don't have to, you can really pick any of them. I'm going to go ahead and solve this equation for x1. And so when I do that, we get 10x1 equals 3x2 plus 2x3. And if I divide here, we get x1 is equal to 3/10 x2 plus 1/5 x3. Now, this is our relationship, and that's great. But now let's write, or let's list our solutions, right? When we're solving a system, we have to say, okay, what is x1? What is x2? What is x3? Well, we can see that x1 is equal to 3/10 x2 plus 1/5 x3. But that's the only constraint we have, which means now we have two free variables. X2 can be whatever it wants, and x3 can be whatever it wants. If I then write that solution as a vector, my first component here is going to be 3/10 x2 plus 1/5 x3. And then my second component is x2 and third is x3. I'm going to pull this apart a little bit. I'm going to split this up as 3/10 x2, x2 and 0, putting all my x2s in one vector, and put all my x3s in the other. So I have 1/5 x3, 0, and x3. And the reason I'm doing that is now in my first vector, I can pull out that x2. So we get 3/10, 1, 0 times x2 plus 1/5, 0, 1 times x3. Notice in this example, we had two free variables. X2 and x3 could be whatever they want it to be. And as a result, my solution now is going to be the linear combination of two vectors this time. And in fact, now I end up with, of course, there are two free variables, so now I have two parameters. So again, if I wanted to, if you don't feel like writing x2 and x3, you could instead say that my solution is going to be 3/10, 1, 0 times some parameter, and I'll just call it t because I'm not feeling very creative, plus 1/5, 0, 1 times some other parameter. I'll call that s. By the way, if you use the letter s, please make it cursive s because otherwise it looks like the number 5. Also, if you use t, try to make that cursive because then it just looks like a plus sign if you don't. So anyway, the point is my solution now has had two free variables, which means that there are two parameters. And in fact, what the result is that my solution was the linear combination of two vectors. Well, geometrically, the linear combination of two vectors results in a plane in R3. Okay, we saw that last lesson. So 2 free variables means now we've got a plane. To summarize here a little bit, if there are no free variables, remember, no free variables means that one unique solution, and if it's homogeneous, by the way, this whole slide is all about the homogeneous. AX equals 0. I don't think I wrote that anywhere. If A has no free variables, then the homogeneous system has only the trivial solution, and the trivial solution is just 0, right? It's just the origin. It's just 1 point in R3. If A has one free variable, then the result is a line in R3 that passes through the origin, and our solution can be described parametrically. X can be written as some parameter t times a vector v1. If A has 2 free variables, then now our solution is going to be a plane in R3, again, that passes through the origin. And now our solution can be written parametrically as some parameter times v1 plus some other parameter times another vector v2. And it's just interesting, it's useful to observe that my solution set, the set of all solutions, is the span of those two vectors v1 and v2. Because what does it mean? What does the span mean? It means the set of all linear combinations of v1 and v2. Well, that's what our solution is. It's the set of all linear combinations of v1 and v2. Because S and T could be any number. Pick a different number for S, different number for T, you get a new linear combination. When we write our answer in this form, or I should say, when there are multiple solutions, and when we write our answer in this form, this is called parametric vector form. So I just want to make sure you guys recognize that, so that if on a test or something I ask you to write your answer in parametric vector form, we understand that what that means is write it as x equals, here, let me just go back here. This would be parametric vector form. Okay. Now, you don't have to use S and T. If you want to leave it as x1 or x2 and x3, I have no problem with that. That's okay. But it means write your solution as a vector times one parameter plus another vector times another parameter, if there are two parameters, of course. But what you call the parameters is up to you. Call them T and S, call them x2 and x3. I don't really care. Okay. So this whole slide is all about parametric equations. I'm sorry, that's not what I meant to say at all. This whole slide is about homogeneous equations. That's what I meant to say. Now let's look at non-homogeneous. Okay, so non-homogeneous means that now the right side is non-zero. So now that equation AX equals B, we can call that non-homogeneous. Well, let's describe the solution set of this one. Now, it is worth observing that the left side of this system is actually the same as the left side of the system that we solved at the very beginning. But we still need to go through from the beginning, because what I mean is we can't just jump to the reduced echelon or the reduced form. No, that's right, reduced echelon form. We can't just jump to that, because when we got the reduced echelon form, we did a lot of steps to go, from one matrix to another. Earlier, it didn't matter. The right side didn't change because they were all zeros. Now, each of those steps will affect the numbers on the right side. So I still need to go through that same process once again. So let me write the augmented matrix, 3, 5, negative 4, 7. The advantage of having done this before is at least now I know to expect one free variable. And also I know and I kind of have an idea of what I'm going to do to go from one step to another. So at least I don't have to make those kinds of decisions. I just have to do the work. So the top row is fine. If I add the first and second rows, I get 0, 3, 0, 6. If I do negative 2 times the top plus the bottom, I get 0, negative 9, 0, negative 18. So the top row is 3, 5, negative 4, 7. As I did before, I'm going to divide the middle row by 3. So we get 0, 1, 0, 2. And notice once more, if I multiply the middle row by negative 3 and add the bottom row, I'm sorry, multiply the middle row by positive 3 and add the bottom row, we just get a bunch of zeros, which is good. It means that there is going to be, because remember, it, we had a free variable in the in the earlier example, but if this number here had been non-zero, we know that there's going to be no solution, right? If this number here had been non-zero, then we would have had a pivot there, which means there's be no solution. So fortunately, there are going to be, we know this now, there's going to be many solutions. Let me put this now into reduced echelon form. So let's see, second and third row are fine. All zeros, there's definitely nothing to do there. I'm going to multiply the middle row by negative 5 and add the top row. So we get 3, 0, negative 4, and negative 3. And then finally, as we did before, divide the top row by 3. We get 1, 0, negative 4 thirds, negative 1, and then 0, 1, 0, 2, 0, 0, 0, 0. Okay. So we've now got this into reduced echelon form. I do want to remind you, by the way, that in the last lesson, we didn't put anything into reduced echelon form once, because in the last lesson, the only question we asked was, where is there a pivot? And if we want to know where is there a pivot, echelon form is good enough. But if we want to actually find the solution, reduced echelon form is an easier way to go, an easier option. All right, the top equation tells me that x1 minus 4 thirds x3 is equal to negative 1. The middle row tells me that x2 is equal to 2. And so now, and I'm doing the same thing I did before. Let's now write our x1, x2, and x3. So x1 is going to be 4 thirds x3 minus 1. X2 is equal to 2, and x3 is our free variable, so x3 equals x3. Okay, if I now write my answer as a vector, we're going to get 4 thirds x3 minus 1, 2, and x3. Now, kind of like we did before, remember in the earlier example, when there were both x2s and x3s, we split up into two vectors. One of the vectors had the x2s, one of the vectors had the x3s. Well, here, I'm going to make one vector that has the x3s. So that would be 4 thirds x3, 0, x3. And then I'm going to add to that a vector that has no variables. So that would be negative 1, 2, 0. And then one last thing I'm going to do here, I'm going to pull out the x3 from the first vector. So we're going to get 4 thirds, 0, 1 times x3, as we did before. I'm just going to call that t because that's going to end up being our parameter, plus this vector, negative 1, 2, 0. All right, so please notice when we solved this non-homogeneous solution or non-homogeneous equation, notice that our solution was exactly the same thing as our homogeneous solution. We just added one extra vector to it. So it's just interesting to make that observation. In fact, once again, we're going to generalize this in just a second. But the observation is that our non-homogeneous solution was nothing more than our homogeneous solution plus one extra vector. To summarize here, ax equals b will have no solutions if ax equals b is inconsistent, right? That's basically no solution, same thing. Ax equal b will have only one solution if the homogeneous system had only the trivial solution. So that's an interesting observation here. So ax equals b has only one solution if ax equals 0 has only the trivial solution. Okay. Which, by the way, kind of makes sense because remember what we said. This has only the trivial solution if every column has, I'm sorry, if there are no free variables. If ax equals 0 had only the trivial solution if there are no free variables. Well, that means that ax equals b will also have no free variables, which means, as we learned a couple lessons ago, that means that there's going to be only one solution. So this really does this matches with what we've been discussing here. And then ax equals b will have infinitely many solutions if the corresponding homogeneous system also had infinitely many solutions. The solutions will be one vector plus a linear combination of the vectors that satisfy the corresponding homogeneous solution. This example here is the one we just did. Remember, this was that homogeneous solution. And so the non-homogeneous solution is the same, but then we just add one extra vector to it, p. And the result is going to be, well, t times v1 would be a line through the origin. So adding p is going to shift us away from the origin. I'm going to tell you right now, knowing these two things is not all that useful. I mean, it's kind of nice because now we kind of know what to expect, but it doesn't really help us do the problems. Really, you're still going to have to do what we did in the last example. You're still going to have to find the augmented matrix, put it into echelon form or reduced echelon form, solve for x. You're still going to have to go through all that process. So I wouldn't focus too much effort on memorizing these forms or anything. This is what we can expect this solution to look like, but knowing that doesn't actually help you do the problem. So I wouldn't stress too much. But let's think about that for a second. Let's prove that last result. So what does that last result really say? Let's make these assumptions. Let's assume that x equals t times v1 is the solution to ax equals 0. And let's assume that p is a solution to ax equals b. Okay, so we're assuming that t times v is a solution of the homogeneous, and that p is one extra vector that is a solution to the non-homogeneous. And let's show that adding those together is also a solution to ax equals b. Okay, so let's prove that. Let's show that that's the case. Well, so what I'm going to do is I'm going to start with ax equals b, and I'm going to take this thing here and I'm going to plug it in. So I'm going to do a times tv plus b, plus p, excuse me. And I want to know, I'm going to put a question mark there. I want to know if that's equal to b. Okay, we can distribute. So a times tv plus a times p. We want to know if that's equal to b. Now, let's take a look at this for a second. Didn't we say that t times v was a solution to ax equals 0? In other words, if I take tv and I multiply it by a, the result is going to be the 0 vector. Further, I assume that p was a solution to this equation. In other words, if I plug in p for x, if I do a times p, the result is going to be b. Right? If tv1 is I'm using subscripts here, sorry. If t times v1 is a solution to ax equals 0, that means that a times t times v will be 0. Likewise, if I assume that p is a solution to ax equals b, that means that a times p will be equal to b. And certainly 0 plus b is just b. So it works. So if I took that sum and plugged them in, then the result is a solution to that non-homogeneous ax equals b. Okay, so there's our homogeneous and non-homogeneous systems. Now, let me introduce another concept here, the idea of linear independence. So a set of vectors, v1, v2, etc., a set of vectors is linearly dependent if there exists some constants, x1, x2, up through xp, where they're not all zero, but the result, when I combine them using those coefficients, is zero. So these are linearly dependent if basically I can do a constant multiple times v1, a constant times v2, and so on. And when I combine them all together, I get the zero vector. Again, that's always going to be true if my x's are all zeros. So we need to linearly dependent means it's possible to find non-zero vectors that will still work for us. Let me give you a really simple example. What if I gave you this vector? Okay, I'm not feeling very creative. Yeah, all right, let's be creative here. 1, 2, 3. Nope, not being creative. That's okay. 1, 2, 3, 4, 5, 6. And how about 2, 1, 0? Okay, let's say we have these three vectors, and I want to show that these are linearly dependent. Well, just because the way I created this here, if I did, if I used a coefficient here of -2, and I used here a coefficient of 1, and here a coefficient of -1, if I multiply the first one by -2 plus the second one, and then plus -1 times the third one, if I did everything here correctly, I'm going to get a result of 0, 0, 0. So these are linearly dependent because I can find these coefficients such that the combination of those three vectors is the zero vector. Now, it's not always obvious where to find those coefficients, and that's part of the question we're going to be asking today. But that's what we mean by linearly dependent. It means there's some relationship that results in the zero vector. And this equation is called the dependence relation, linear dependence relation. So if I say if these three vectors are linearly dependent, find me a dependence relation, this is what I'm looking for. It basically means show me the equation along with the coefficients that result in the zero vector. So that's the linear relation, linear dependence relation, excuse me. And if there is no such relation, if there's no way for me to find coefficients other than all zeros, then we say that the set of vectors is linearly independent. Okay, so let's determine if these vectors are dependent. And I guess I don't have enough space to write out the whole question. So here's the question. Determine if these vectors are dependent. If they are dependent, find a dependence relation. Now, let's think about this for a second. I need some vector times 1, 2, 3. Oh, wow. Okay. Let's pretend I didn't do the last example for a second. I can't believe I did that. This is hilarious. That's okay. Let's find the rigorous way instead of the one where I tell you what the answer is. So x1 times this plus x2 times that plus x3 times that equals 0, 0, 0. This is the question we're asking, is find those coefficients so that this combination gives us the result of 0, 0, 0. Now, look at that equation for a second. Isn't that just a vector equation? And if that's a vector equation, we know how to find the corresponding augmented matrix. So let's find it. 1, 4, 2, 0, 2, 5, 1, 0, 3, 6, 0, 0. Basically, determining if these vectors are linearly dependent is the same as determining if, hold on, I have to think about what I was saying here. Determining if these are linearly dependent is the same as determining if this is basically finding x1, x2, and x3. So it's determining if this homogeneous system has a non-trivial solution, right? Trivial means all the variables are zero. Well, if all the variables are zero, then the set is then the vectors are linearly independent. So if I get anything other than anything other than a trivial solution, then the vectors are linearly dependent. Okay, so let's continue. Let's solve the system. Top row is fine. Multiply the top by -2 and add the second row would give me 0, -3, -3, 0. Multiply the top by -3 and add the bottom row would be 0, -2. Nope, that's not right. Hold on, times -6. -6, 0. I'm going to do a couple of things here. I'm going to divide the middle row by -3. So we get 0, 1, 1, 0. And if I do the second row times -2 plus the bottom row, I get 0, 0, 0, 0. Okay. Right away, I can answer one of the questions here because right away I can see there is a free variable. There is a column with no pivot. So because there is a free variable, right away I know that the homogeneous system has a non-trivial solution, which means that the set is linearly dependent, right? Trivial solution means all the coefficients have to be zero. So non-trivial means that there are some coefficients that will work, which means that the system is linear, the set of vectors is linearly dependent. That's great, and that's one of the questions. But, and only because the problem said find a linear dependence relation, I have to keep going. If the problem had just said determine if the vectors are dependent, I can stop. Because as soon as I see there's a free variable, my question is answered, is dependent. But because it also says find a dependence relation, now I need to keep going. Okay, so now I need to put this in reduced echelon form. So the middle row is fine. Bottom row is certainly fine. Multiply the bottom row by -4 and add the top row. It gives me 1, 0, -2, 0. Now it's in reduced echelon form, so now I can say x1 minus 2x3 is equal to 0. x2 plus x3 is equal to 0, and of course x3, so I don't need to write that yet. Come on. Erase. Okay, and now if I write out my solutions here, x1 is equal to 2x3, x2 is equal to -x3, and x3 is equal to x3. So my solution vector here, if I put this in parametric vector form, it's going to be 2, -1, 1 times t. Or again, if you want to say times x3, nothing wrong with that. Now, that's great. But in the context of our problem, those three parts of that vector give us the coefficients we're looking for. The problem says find a linear dependence relation. Well, that means find the coefficients, and we've just found them. 2 times x1 plus -1 times x2 plus 1 times x3 is equal to the 0 vector. That is the linear dependence relation, and so that's the second part of our answer. So we had to keep going to figure out what that vector was that we were looking for. By the way, if you write this, just because people might be wondering, if you wrote this as 2x1 minus x2 plus x3 equals the 0 vector, also perfectly acceptable. I don't care if you put the -1 and the 1, it doesn't matter. I forgot to put the vectors here. Okay, so we've got our answer. Cool. So let's consider this dependence relation. So please note that this is the same as our homogeneous equation ax equals 0. Okay, we just discussed that, where the vectors are the columns of A. So we didn't really talk about that, but notice that when I created this vector A, the left side of my augmented matrix, the columns of A were basically just the three vectors we were asked about, v1, v2, and v3. Okay, the following statements are equivalent. We have another one of these. So first off, ax equals 0 has only the trivial solution. Great. Number two, the columns of A are linearly independent. Okay, so that kind of matches the first half of this lesson with the second half of this lesson. The idea that ax equals 0 has only the trivial solution means that the weights, the variables, are all have to be zeros. And if they all have to be zeros, then the columns of A, those vectors, are linearly independent. Okay, three here, the linear system with augmented matrix A0, let me put the little line there, has no free variables, right? That that links directly back with statement 1, right? Ax equals 0 has only trivial solutions. Has only the trivial solution if A has no free variables. And that also means that A has a pivot in every column, right? Steps 3 and 4 are the same thing, right? If there are no free variables, that means that there's a pivot in every column of A. Okay, so these are all basically the same thing. Okay, so let's determine if these vectors are dependent. Now, notice that in these four statements, notice the statements 2 and 4 actually don't even care about the 0. They don't even care about the augmented matrix. Statements 2 and 4 are only interested in the coefficient matrix A. So let's think about that for a second. If I want to know if these three vectors are dependent, let's just form vector A. So 0, 1, 5, 1, 2, 8, 4, negative 1, 0. So vector A is made up of, or sorry, the columns of A are these three vectors, v1, v2, and v3. Now, statement 2 and 3 basically say that the columns are independent if and only if A has a pivot in every column. So to answer this question, instead of setting up the augmented matrix, instead of setting up the homogeneous equation, I can just look at A. I can just say, oh, okay, well, there's A. Is there a pivot in every column? If the answer is yes, then the vectors are independent. If the answer is no, then the vectors are dependent. So let's do that. So we've got A. Let's determine where the pivots are. I'm going to switch the top and the first and second rows. So we get 1, 2, negative 1, 0, 1, 4, 5, 8, 0. Top row's fine. Second row's fine. I'm going to multiply the top by negative 5 and add the bottom. So we get 0, negative 2, 5. I'm going to so first, second row, fine. Multiply the middle row by 2 and add the bottom. We get 0, 0, 13. And I can stop here, right? The question is simply, is there a pivot in every column? And the answer is yes. So we see a pivot in each column. Therefore, the columns are independent. I don't mind if you abbreviate. And by the way, on tests, I will be asking you to do certain things like this. Not solve a problem. There will be some problems to solve, like, solve the system of equations. But there might be ones where say, determine if this is true, show if this is true. If that's the case, you need to explain your answer. You can't just say, okay, here's my matrix, done, move on to the next one. You need to show me what conclusion you're making. What do you observe and what conclusion can you make from that? I observe that there's a pivot in every column, and therefore I can conclude that the columns are independent. Okay, let's look at a couple of examples here. So let's determine if these vectors are linearly dependent. Um, okay, so to answer this question, there are a couple of ways we can do this. Now, there's nothing wrong with setting up the matrix, et cetera, et cetera, et cetera. But let's think about something else. Remember, linearly dependent means that if I did C1 times 3, 1 plus C2 times 6, 2, the result would be the zero vector. Okay. Let me rearrange stuff a little bit. C1 times 3, 1 equals negative C2 times 6, 2. And then I'm going to divide everything by C1, so I get 3, 1 is equal to negative C2 over C1 times 6, 2. So remember the question. These vectors are linearly dependent if I can find these coefficients C1 and C2. In other words, these two vectors are linearly dependent if x1 is equal to some constant multiple of or v1 is some constant multiple of v2. So, and notice in this case it is. Notice in this case, as long as that coefficient was 1/2, half of v2 is equal to v1. So the answer is these are dependent because v1 is equal to 1/2 of v2. Or you can say v2 is equal to 2 times v1. It doesn't matter. But the point is there's some relationship between those. Using the same logic, the only way that these will be dependent is if one of them is a multiple of the other. In this case, that is not true. So these are independent because v1 is not a constant times v2. So the point of this, and actually the next bit of this lesson, really the rest of this lesson is there a quick way, or are there any quick ways to identify if vectors are dependent or independent? Okay, and so because certainly we could go through this whole process to decide if they're dependent or independent, but are there any quicker ways? Okay, are there any shortcuts? Well, this leads us to a shortcut. This leads us to the shortcut that two vectors are linearly dependent if one of them is a multiple of the other. Okay, so two vectors are linearly dependent if one of them is a multiple of the other. Geometrically, these two vectors are linearly dependent because they lie on the same line. The bottom are not because they don't lie on the same line. Okay, so two vectors are linear. So two vectors are linearly dependent if one of them is a multiple of the other. Important observation though, that only works if there are two. Okay, if you've got three vectors, you can't just pair them up and, oh, these aren't multiples, therefore they're independent. It doesn't work that way. If you have more than two vectors, this trick does not work. But if you have only two vectors, they're dependent if one of them is a multiple of the other. So that's a nice little shortcut. Next observation here. A set of two or more vectors are linearly dependent if and only if at least one is a linear combination of the others. Okay, so consider this. Describe the set spanned by u and v, and then let's explain why a vector w in the span, why a vector w is in the span if and only if u, v, and w are linearly dependent. Okay, so let's start with that. Every vector in this span, and I'll give it a name, I'll call it w because that's what we're doing. Every vector in the span is c1 v1, or sorry, c1u plus c2v, right? The span means the set of all vectors that are linear combinations of u and v. So w is a constant times u plus another constant times v. Now, the question is, if I take all three of those vectors, is that set linearly dependent? Well, let's think about this for a second. let's consider the dependence relation. So C1, let me use different letters here. So we've got x1 times u plus x2 times v plus x3 times w. And I guess I could put a question mark here, but basically the question is, can I find u or x1, x2, and x3 that'll work for this? Let's plug in. So x1 times u plus x2 times v plus x3 times. I'm going to replace the w with c1u plus c2 times v. We are making the assumption that w is a linear combination of u and v, so I can make that substitution. Let me distribute a little bit. So x1 times u plus x2 times v plus x3 c1 times u plus x3 c2 times v. And then rearranging a little bit, the coefficients for u would be x1 plus x3 times c1. And then the coefficients for v would be x2 plus x3 times c2. Okay, now I want to remind you, my goal is to find x1, x2, and x3. Or rather, my goal is to show that x1, it's possible to find x1, x2, and x3 that are non-zero for this problem. Well, notice if the left side of this equation is equal to 0, that means that the coefficient for u is going to have to be 0, which means that x1 is equal to negative x3 c1. And the coefficient for v will be 0. So x2 plus x3 should be c2 is equal to 0. So x2 is going to be negative x3 c2. So one more time, the question is, can I find values for x1, x2, and x3? And the answer is yes. x1 is going to be negative x3 times c1. x2 is going to be negative x3 times c2. And x3 can be whatever it wants. Pick any number you want for x3. Okay, don't pick 0. But if you pick any other number for x3, plug it in here, and you're going to find a number you can pick for x2, no matter what you pick for c2. And plug it in here, and no matter what you pick for c1, you're going to get an answer for x1. These are linearly dependent because it is possible to find those coefficients. And again, as long as we pick x3 to be non-zero, we're going to be able to find those coefficients that show that these three vectors are linearly dependent. Okay. Now, it's worth remembering, actually, I'm going to come back to that in just a second. So we've got this. So if we have two vectors, if we have a vector that's in the span of two other vectors, then all three of those vectors are linearly dependent. Okay. If a set contains more vectors than there are entries in each vector, then the set is linearly dependent. So here, each vector has 2 entries, but there are 3 of them. Okay, show that this set is linearly dependent. Well, remember, one of our ways to show dependence is the augmented, or is to form vector A. Vector A has the columns that's each of these vectors, 2, 1, 4, -1, -2, 2. Now think about this for a second. We said that the columns are independent if and only if there's a pivot in each column. of A? Well, look at vector A. There's no way for there to be a pivot in every column. Listen, even if there's a pivot here, okay, maybe the other pivot is here, maybe it's here, maybe it's none of them, I don't know. But the point is, there is no way to have a pivot in all three columns if there is only two rows, right? Each row can only have one pivot. So right away, there's not a pivot in each column. Therefore, the vectors are linearly dependent. That's it, right? There, you got too many vectors. That's it, right? So if you have more vectors than you have entries in each vector, then the set is automatically dependent. Okay. One more observation here. Actually, I don't want to go to that. If a set contains a zero vector, it is automatically a dependent set, right? Consider this. Let's say you've got three vectors, u, v, and the zero vector. Okay. Now remember, they're linearly dependent if you can find those coefficients. And the result is zero. Well, remember, linear dependence means you can find coefficients and they're not all zeros. There's nothing wrong with making some of the vectors zero, or some of the coefficients zeros. If you let this coefficient be zero and this coefficient be zero, literally pick any other number for this coefficient, like 5. This is a linearly dependent set because I found coefficients. They weren't all zeros, but the combination resulted in the zero vector. So if you have a set of vectors where at least where one of the vectors is the zero vector, it is automatically dependent. So a couple of quick examples here. Determine if the set is dependent. Okay, well, right away, there's more vectors than there are entries in each vector. Which means that this is automatically a dependent set. Okay. This one, it's got the zero vector. Therefore, this is a dependent set. And this one, remember, if there are only two vectors, if one of them is a multiple of the other, and let me just call these u and v, if one of them is a multiple of the other, then they are automatically dependent. Well, I'm going to observe that u is equal to, or how about -3 times u is equal to v, which means that automatically these are dependent vectors. Now, one more time. These are shortcuts. These are nice, quick ways of identifying dependent vectors. What if this one hadn't been there? What if it had just been those three? Well, now there's no quick way. Now you need the to create the matrix and determine if there are pivots in every column and the whole deal. But these are just nice, quick little shortcuts that avoid us having to do all that. Anyway, that is the end of the lesson. Thank you very much for watching.